Well, hello everyone, and welcome to the September 2025 edition of the St. Louis Java Users Group. And for those who don't know, the St. Louis Java Users Group is an informal group. Our first meeting was May of 1997. Attendance is free. There is no formal membership list. Normally, we try to meet on the second Thursday of every month except December, when there is no meeting. When we meet in person, you can join us for food and social at 6 p.m. and the meeting starts at 6:30 p.m. And when we meet in person, our normal meeting location is at the Object Computing Incorporated Training Room, and we're located at 12,140 Woodcrest Executive Drive, Suite 310, and that's in St. Louis, Missouri. I'd like to introduce the other members of the St. Louis Java Users Group Steering Committee. So from left to right here, we have Zach Klein, Bruce Alspaugh, that's me, Robert Levitt, and Ted Doyle. You can reach all of us on the steering committee if you send an email to that address at the bottom of your screen. That's javasigsc@googlegroups.com. The St. Louis Java Users Group would not be possible without the support of our sponsors. Object Computing Incorporated was our founding sponsor, and they're still with us today. They've sponsored the meeting rooms, they sponsor food, they're sponsoring the streaming system that we're using to deliver this to you. So they've bailed us out many times and kept us going more times than I can count. At the end of this meeting, we'll be raffling 2 Manning ebooks, and I believe 4 JetBrains licenses will be available, but you must be present to win. Online. So after the meeting, stick around and maybe you'll get lucky and win one of those things. I'd also like to thank Lee Bobbitt, and he has sponsored the Meetup subscription. It's free for you to use the Meetup site to RSVP for our meetings, but it does cost the group about, I think it's about $30 a month for us to keep the Meetup page on that site. And Lee has kindly sponsored that for us. So thank you to all of our sponsors. Manning, one of our sponsors, does have a 40% off any product discount code. So when you go to their online store at manning.com, you can put in that coupon code JUG13 and get 40% off on your purchase. We have some great presentations coming up. On October 9th, it'll be what's next for WebAssembly on the server. So tonight we're going to be talking about how to do Java bytecode in the virtual machine. This is going to be WebAssembly bytecode that runs inside of your web browser. So another kind of bytecode. On November 13th, we're going to do a build system. That's simpler Java build tools with object-oriented programming. And our speaker will be coming all the way from Singapore, and he has put together a build system called Mill Build. And he's going to teach us what that thing can do as compared to, say, Maven or Gradle, which is what a lot of Java developers use. So if you'd like to keep up with our presentation schedule, that's easy to do. Just go to our Meetup group, that's meetup.com/gatewayjug, for updates to the presentation schedule and location. And you can already go ahead and RSVP for those meetings if you'd like. And this meeting is being recorded, and as soon as I get the recording and everything edited with all the bloopers edited out, I'll post it on my YouTube channel. That's youtube.com/@Bruce Alspaugh, my name. Now, if you're interested in giving a presentation or sponsoring the user group, just send us an email at that address again that I mentioned before. That's javasigsc@googlegroups.com. So enough about me. I'm going to turn things over here to our speaker tonight, and that's Jason Clark of GitHub, and he's going to tell us about how to get a better understanding through bytecode in the Java virtual machine. And so what I'm going to do is I'm going to see if I can click this button to stop presenting so that Jason can take over the screen and take it away. So take it away, Jason.
All right. Everybody seeing the slide? Yeah?
Yeah, it looks good to me.
Okay, cool. Awesome. Well, thank you for joining me here tonight. So, as Bruce introduced, the title of this talk is Better Understanding Through Bytecode. This talk actually came out of, so I work for GitHub now. I've worked there for about 1.5 years. This came more out of my time with New Relic, where I was doing a lot more back-end Java. There's not a lot of that around GitHub these days. But
just a moment, I got to do something here. I'm trying to watch the presentation.
So, anyways, this is some interesting stuff that I learned kind of at my prior employer, but really enjoyed digging deeply into it. So, let's get started. A lot of times when we're trying to understand code, when we're trying to understand problems, the way that we go about that is abstracting away, right? So like architectural diagrams, right? Step back from the code, get a bigger picture view, be able to see the bigger set of things. And, you know, I used to be more in an architect position. Drawing these sorts of diagrams was my bread and butter. But I think that there's actually certain types of problems and certain times that going the other direction really helps. And that's what this talk is inspired by, is some things where I feel like you get a very unique understanding by delving deeper instead of trying to back up and look at things through a bigger lens. So that's exactly what we're going to do tonight. We're going to look at first talking about how the JVM actually runs bytecode, and talk through some of the specifics of a few of the basic cases, so that we can really understand how bytecodes are interpreted and how that works. So we're going to get a little bit of tools and enough knowledge that you could build off of it from there if you wanted to. But then we're going to take those tools and we're going to use them to understand about certain problems and structures in programs. So we're going to look at some concurrency related stuff, some things related to recursion, and then last but not least, coroutines actually from Kotlin, and a little bit of comparison with Loom there. So looking at all of these, but not from a big picture lens, from a what does the bytecode tell us? What can we learn by looking at the lower level of what's going on? All right. What I really want people to take away from this talk, even if you don't remember the bytecode, the examples, the details, the real inspiration here is that you can understand the level that's below your current comfort level. You can dig down deeper. It's all just computers. We can understand it. And you don't have to understand all of it for it to be useful to start digging. You don't need to understand the whole thing now. We are not going to introduce the 200+ bytecode operation codes that are in existence. We're going to have a handful of them, but those are going to be enough for us to be able to do something interesting. So with that intro, let's talk about how the JVM actually runs our code. This diagram kind of gives a high level picture, and will let us sort of find our way to the level that we're going to be looking at the most. Most of us, you know, we write Java, maybe write some Kotlin. There will be a little later on, or potentially other languages. Those code files are compiled and result in class files. The JVM really only understands class files. That's what it runs. And it doesn't really care what language or where those came from. Those class files are what's important. When your JVM is executing, those class files get loaded up. There is potentially some transformation that happens on them. This is how a lot of like auto instrumentation and other things happen. But that class file basically turns into a set of bytecodes that are then interpreted when the program begins running. So that bytecode gets stepped through, executed very much in a style that we'll actually mimic by hand tonight. Now, once that code has executed for a little while, the JVM is paying attention to how long things are run, what methods are important, and it gets to work on JIT compiling it. And it turns those bytecodes into machine code, which then is super fast and supports Java being the very high performance environment that it is. We're not going to talk any more about that step. We're going to stop at the bytecodes and how those are interpreted. But know that the machine code that ends up getting JITted is functionally equivalent to what we're talking about here. It's just way, way faster. So If you want to dig in more to this topic as well, after we've talked through and kind of given the high level, there was a great talk by Ben Evans several years ago at JBCN, which is since rebranded, where he goes into a lot more detail about more of the bytecodes. And so I would encourage you to go think about looking up that presentation if you're interested. And another great resource where we delved into that a lot is the book, The Well-Grounded Java Developer, the second edition particularly that I authored with Ben. There's a whole chapter on bytecode, and there's a lot throughout the book that is also part of the inspiration of where this talk came from. So those are some great resources if you want to go deeper. But to begin with, let's get our feet wet with seeing how some of this bytecode interpretation works. The place that I like to start is that we're going to talk about two stacks. There are two really important stacks that exist with JVM and that we need to think about when we're talking about bytecode interpretation. The first one is probably pretty familiar to most Java developers, and that's the call stack. Now, most of us see this when we make a mistake and an exception gets thrown. You might see it in your debugger as well. But this is the chain of the methods that have been called. This just says, we called the method main, then it called first, second, and third. That's what that stack sort of represents, is those methods in sequence for us. Each of those methods we refer to as a call frame. And that call frame has data associated with it. And so a lot of what we're going to do tonight is looking at sort of things that are happening at this call frame level while we're in that sort of space. So in the layout that we've got here, you've got the method that you're executing. There are then slots which are used for passing arguments in and for holding local variables. So this call frame has storage sort of associated with it for that purpose. And then there's the other stack, and this is the evaluation stack. This actually turns out to be where the JVM does its major computation. This is where most of the actual calculating that goes on in a Java program happens in these evaluation stacks within the call frame. So the JVM, in terms of virtual machines, there's a couple different styles of them, but the JVM is a stacked machine. And so we'll step through what that means and see how that proceeds. But there's vitally at the heart of each call frame, there's a stack that the JVM is using to do its work. So interacting with that evaluation stack, we have to know about bytecodes. So let's learn just enough bytecode reading to be able to navigate this sort of space. Most of my examples here are going to be fairly simplistic, and part of that is because bytecode, while not deeply complicated in some ways, is really, really long and verbose. It's written for computers. It's not written for human beings to be sitting there and reading as a first-class thing. So it'll make it easier for us to sort of take these small pointed examples, but know that all of these tools and techniques apply to any Java program that you might have. So our first method that we're going to take a look at is an instance method called add on a class called add, and it does exactly what you would think. It adds our two numbers together. Now, if we've compiled this class down to a class file, we can run a utility that comes with the JDK called JavaP on that. And specifically, we care about the -c parameter to that when we run it. If you run JavaP just by itself, it'll show you some high-level stuff, method lists, but it doesn't show you all of the bytecode. You have to say -c to ask it, hey, give me the code. And so here is the first part of the output that comes from our teeny tiny little class file. And our first step when we sort of encounter this should be look for the things that we recognize, right? Like we said, we don't need to understand everything, but we want to find the pieces that we know something about. And actually down towards the bottom of this display, we see something that's familiar. There's our add method. That's the, this is inside of the class. There's the add, and then the bytecode actually follows that. So that sort of grounds us in what we want to look at. So having found our bytecode, let's go and let's look at what would be happening in our call frame while we execute that particular add function, add method. So we're going to call it with two numbers, 10 and 32. And so we can see over on the left, those local slots that we were talking about. First off, because this is an instance method, the object itself is always in slot 0. And so that is this for the object. So that is present in the locals. And then the arguments are placed following that. So slot 1 has the number 10, which we were passing in. Slot 2 has the number 32. Okay. Over on the right, we have what the bytecodes are. So there are 4 bytecodes that come out of that plus method that as we had written it. The first 2 are of a form where they say load in the name. Now, there are a lot of different flavors of these loads. The I in front of this particular one, so I load _1, means that it's dealing with an integer primitive type. All of the primitive types that are in Java have a representation with load. Also, the _1 is a shortcut to say load from slot 1 because that's super common. You can pass an I load with a second byte that follows it that says the location to go read from, but that would take up 2 bytes. And so because slots 0, 1, 2 get accessed so frequently, they have single byte codes that represent that. All right, so let's step through and exercise this as if we are the JVM. Let's use our evaluation stack and see what the execution of these actual bytecodes do. So the first one is iLoad1, and what that will do is that will take the number that is in slot number 1 and it will push it onto our evaluation stack. So we now have the number 10 on the top of our evaluation stack. When we execute iLoad2, unsurprisingly, we now push a 32 on top of that 10. So we now have those 2 entries on our stack. The next bytecode that follows that is iadd. What that will do is that will pop the top 2 elements off of our stack, add them together, and push the result back onto the stack. If any of you have used, HP reverse Polish notation calculators before, this will be very familiar. That's how these operations happen there. And this is how almost all of the JVMs work at the bytecode level works. It works by pushing and popping things off of the stack and running bytecodes which use those in certain prescribed ways. All right, so our result from that add operation has been pushed onto the stack, and then we return that says, hey, return to the call frame above me with the value which is sitting on top of my stack at this point. There it is. We have executed the bytecode for our first method to be able to understand. There's a couple more commands that it's going to be good for us to have our hands around before we can do a few real examples. So the next thing that we'll do, we're going to take a string and assign it into a local variable. And this will show us a couple more of those pieces that we're interested in. So the first bytecode that comes out of this is one called LDC, and that stands for load constant. And it has that numeral 2 there, and then there's a comment that tells us that makes it understand that this is the string we're talking about. Part of the class file format is that it has a constant pool, and that constant pool contains a lot of sort of metadata that the Java program needs to run. So all of your strings, your classes, your methods, all of those have a representation in that constant pool, and they're referred to numerically. So for this particular program, number 2 as the entry in the constant pool is a string. We'll take a look at what that actually looks like in more detail in a moment. But when we call LDC as the bytecode for it, it will push that onto the evaluation stack. Like we said, everything revolves around things going on and off of this stack. After we've put that onto the stack, this calls a store_1 bytecode. So the A is an object reference, so essentially like a pointer to it that it will store. Store is the opposite of load. So where load was taking things out of slots, this is putting things into slots. And so we're taking slot number 1 to represent that local variable that we were defining within our method. This method is void on the return, so it simply says return at the end of it. We don't actually do anything. There's no value coming back. So we just say return to get out of the method. So constant pool, this is a little bit more about what it looks like. So when you run Java P, in addition to the -c parameter, if you provided a -d, it will also emit that constant pool. And there's a lot of interesting stuff in there to dig around in. So you see method reference shown here. Our string hi was represented there. It's actually separated. There's an indirection where it has a UTF-8 entity in the constant pool that the string just refers to. So it's a fun place to sort of look around, and you'll see various pieces of your Java program that you will recognize in that constant pool. All right, so we've got one more set of sort of bytecodes that we need to do before we hit our first real example, and that is instantiating objects. That's the heart of Java as a object-oriented language. So when we do a new on an object and assign it to a local variable, this is what the bytecodes come out looking like. And there's a couple of new ones and a couple of things that we recognize. The comments obviously are very helpful that it comes up with for the constant pool. So we can see here that number 2 is referring to the Java class object, and number 1 is referring to this method init in brackets, which we'll talk about in a second what that actually means. And there are pieces that we recognize in this, though. That a_1, which was putting something into a slot to be in a local variable, that's in use here. Our normal return, because this method was void, doesn't do anything with the return values, is also the same as it was before. So let's step through how this one works. Let's create our first object. So the new bytecode, as you would expect, creates a new object. Now, an important thing about it is that when this bytecode has finished, the object is allocated. That is all that it's done, is it has reserved the memory for the object to exist. It hasn't run the constructor. It isn't ready for anything to actually use. Right after it's created that object, it pushes that onto the evaluation stack. And then, interestingly, it dupes it. So there are now 2 copies of the reference to this object on our evaluation stack. And we'll see this time and time again, where there are patterns that the bytecodes emitted by the JVM or by the Java compiler or other compilers will sort of do interesting dupes to put things in just the right order so that when we pop things off, they're where we expect them to be. We'll see why this matters with this next bytecode, which is invoke special. So invoke is the terminology in the bytecodes for running methods. And there are a variety of different invokes that are around. Invoke special particularly is used to invoke constructors. And so that init is the internal name that is given to the constructor for your class. So the constructor for type object is number 1 in this particular class file as it was compiled. And so at this point, once that invoke special has run, then your constructor has run and you still have, and your object is initialized. We can now see why it did that dupe, because the invoke special will consume off of the top of the stack. Now, if we had just newed our object and immediately called invoke special, we would have made a reference to it, and then running the constructor on it would have obliterated the only reference that we had. It would have gone away, and we couldn't use the object. So we had to dupe it so that we would have another copy that we can do something with. In this case, we use our A store to put that object into our local variable, and then we discard it and don't do anything with it. But the bytecodes held on to it for the period of time that we needed to keep our references. Now, that may seem like a very brief introduction to bytecode, but it is enough for us to look at our first example and really start examining a problem from this vantage point of looking down to the bytecode level and seeing what it tells us. So the first thing that we're going to look at is lost updates in concurrent systems. So the class that we're going to look at for doing this example is an account class. So it represents a banking account, has the balance that you initiate it with, and then you can say transfer and pass it another account. It checks to make sure that you have enough money to do the transfer. If it does, then it does the subtraction on your account and the add on the other account to do the transfer back and forth. Now, if you think that this is really good banking code, I would like to appeal to you to not work at my bank, because this has a lot of problems with it. Specifically, the big problem is concurrency. So Java is a natively multi-threaded programming environment, and we can find that if we run a very simple case of running 2 sets of transfers alongside of each other. You might think, if I'm just running 2 of them, it should be fine, right? It couldn't interfere that much. But literally every single time that you run this, you will end up with lost writes. back and forth. So the totals will not come out the way that you expect without some sort of synchronization. And an experienced Java developer knows that like the problem is in this code that's highlighted here. We check whether the balance is better than the transfer amount, but then before we've done the next steps of actually modifying it, another thread might get in there and do some work. I feel like sometimes when we talk about those things, though, it's where the data actually resides, how that interference actually happens is a little vague. It's like, you know, they can interfere with each other, but like what's really, really going on down at the low level? That's what the bytecode's going to tell us. So the output from the transfer method, if we look at it, this will be probably the longest set of bytecode that we will go all the way through sort of step by step. But before we even get into that, I think it's worth pointing out that there's a fair amount of repetition in here. And this repetition is largely around getting and putting the balance field on these accounts. So that is unsurprising, given that like we access the balance several times in the code, as we had referenced, and we access the balance on the other class as well. So get field will expect that it has the object as the thing on the evaluation stack, and then it will get the value of that field and push that onto the stack for us. There is another bit here. So we have that if statement. This is a little new and we haven't encountered it before, but here we have the lcomp and then if less than constructs. Lcomp will do a comparison of, in this case, two longs is what we put there. That's why it has the L instead of an I. Again, would have all of the primitive types for it. And there's a protocol for it being 1 or 0. I don't always remember exactly what value goes which direction unless I stare at it. But that plays well with this if less than. So this says if it's less than, if the result of that comparison is less than the amount, go to byte 29, which we see is our return. So this is our check that says, hey, if you don't have enough in the balance, don't do the transfer and skip over it. Walking through the example, we're going to go through one where there is enough space in the account to do the transfer. So let's take a look at what that is. Once we call our method, we're going to call it to ask to deduct 100 from the account and put it in our other account, which is passed in. So this pointer is in our 0 spot. The 100 being a long, it takes 2 slots to hold on to it there. And then the other object, the other account that we're passing, it takes up the 3rd slot. So we do an A load that gets our object, our current account that we're running this instance method against. When we say get field, it will get the field value for that, push it onto our stack. And then it is loading the amount that we want to take out onto the stack. And then we run a comparison of those. We compare whether the balance is greater than the amount that's being asked. That happens to pass, so we don't jump from this to the very end location. And now we're going to start modifying the accounts. In this case, we're going to A load ourselves, so we get our own object pointer, and we're going to dupe it immediately. We're going to grab the values for the account balance and the amount that we want to take away and subtract them. Just like we do in the code, we see that. And then we go put that field back onto the object. That was why it did that dupe, so we still had that object pointer at the right location when we have the subtraction to be able to put the value back. We do the same sort of song and dance for the other account. We dupe it twice. We grab its current value. We add the value that came in as parameter 1 instead of subtracting it. And then we put it onto the object. And then finally, we're done. So a little bit of object field manipulation going on here, fairly straightforward. But it brings us to the point where we can finally understand where those threads can intersect and interfere with each other. Because that evaluation stack at every point along the way has a copy of the data. It has a copy of what the field value was. It has the copy of the field, the value that we want to put into it. And if we have 2 threads running, every single one of those bytecodes could be interleaved in any sort of order that could happen. There is no synchronization between the bytecode order that those threads go with. So any ordering that you could possibly come up with to do this in these 2 threads is possible down at that level. The interleaving is not at a line of code level. It is at the bytecode level that those things can interleave with each other. So our evaluation stack is kind of the place where we hold those data, those pieces of data, and potentially get stale values. And then when the bytecodes get intermingled in whatever order the JVM decides to execute them in, without synchronization, we can see that all sorts of chaos happens. This is the classic sort of lost update, but seeing it from the bytecode level really makes precise, like, where are those sort of phantom copies of the data that, you know, one side thinks it's this and one side thinks it's that. It's really about, those are the values that are on their call frames evaluation stacks at the time that the other thread is executing. And that's what causes our problems. All right, our next example we're going to look at is, we're going to take a trip down recursion lane, and we're going to talk about specifically something known as tail recursion. So a recursive function is simply a function that calls itself. So here we have a factorial function. This will call itself if it's not 0 or less than 0. It calls itself with 1 less. You know, this will solve sort of the factorial problem, but there's an issue with it if you try to call this with too large of a number, and that is a stack overflow. Now, this will happen because you know, if you give it a number of, honestly, a pretty small size that you would think that you would be able to do these sorts of calculations for, but a recursive algorithm will have that potential. And we now kind of understand why. Right? Like, the reason that this is a problem is because each of those method calls has a call frame, and that call frame is its own independent memory that has to be tracked. There is a cost to each and every one of those method calls in that call frame, and that adds up. Eventually, you have enough call frames, you will exhaust the memory that is available to your JVM, and things will get bad. So this is why people often recommend against using recursive algorithms in a lot of spots, especially if it's for sort of unbounded sizes of data. But they are really elegant. Like, it is something that, you know, it will solve some of your problems very easily and very elegantly in code if you can find a way to make them okay. So one thing that comes in some other languages that helps with this problem is tail recursion. So tail recursion is a structure when the very last method call of a recursive function is the call back to itself. The calls don't initiate anywhere else as long as the last call is a tail recursive, is the method itself, then it will be tail recursive. Now, in fact, our factorial here is not tail recursive, because we call factorial, we get its result, and we multiply it. We do something after we called the function. So it isn't actually tail recursive. And in fact, writing this out and changing the structure of it so that it is tail recursive is really kind of annoying. It's possible, but we're not going to do that here. Instead, what we'll look at is, we'll just take a simpler example, which is obviously tail recursive. So this is the overflow method. You call it, it just adds to the number and calls to itself. Now, it is an important point. Any recursive algorithm that you could come up with, there is a way to write it as a tail recursive algorithm, but it may just not be as convenient or as pretty. All right, so let's step through what happens with this fail call recursion method that we've come up with in Java. So we'll pass in the integer, the number 0 for our first thing. So we do a load that loads it onto our stack. It adds 1, like it was meant, like we saw in the code itself. Once it has added 1, it's got the value there ready to invoke the next method. And that next method is itself. So that's the recursion happening. That will cause a new call frame that will receive 1. And we never hit the return. So this return and these will never get hit, because this method just unconditionally calls itself again. This will run until we run out of space and Stack Overflow. Now, that's the story in Java. And sadly, that is the only story in Java as far as this is concerned. Tail recursion is not supported in the language itself. However, in Kotlin, there is actually a way around this, because there is a keyword, tailrec, which you can put onto a function to let the compiler know that this is a tail recursive algorithm and that you would like to treat it as such. So let's take a look at what the bytecode looks like for this. Now, it's Kotlin, not Java, but it all just emits bytecode. And the end results of that are not that different from what we were seeing before. But we'll get to see a trick here of how this tail recursion avoids the problems of stack overflows. So when we get started, the number again that we pass in needs to get loaded. That's our very first step. But instead of taking it and adding to it immediately, this method, as it's been compiled, is going to take that and it's going to put it off into a local for us. It's going to hold on to that sort of in its scratch space, which is kind of interesting. Once it's put it there, it reloads it from there onto our stack, actually puts the one on the call stack and adds. So it does the addition that we had talked about before, and then it's storing it back to that local location. Then we finally see why it made that local spot and why we're actually no longer a recursive function in terms of calling methods, because the next step that it does is it says go to byte 2. So this just jumps back to the beginning of the method without actually making another method call or making a new call frame. So this will be able to run without any stack overflows. This will run, in fact, it will run, I said infinite, it would run until it overflows the integer in this case, but we avoided the problem that we had where we were hampered by the depth of the call stack that was in play. And I feel like this is an interesting outcome from this, because it kind of strings a couple of different things together. So one of them, like talking about the recursive functions and the fact that you can rewrite them as tail calls, you can write it tail recursive. We just showed that the compiler can figure out how to turn that tail recursion effectively into just a loop. And that tells us that the bytecode is letting us know that, like, recursion is just fancy looping. It's just looping with some methods to make that happen along the way, which is kind of interesting. You know, people think of it sometimes as sort of an esoteric CS topic, but it's really just a fancy sort of loop that we're dealing with. So that's what the bytecode can tell us about recursion. So having dabbled a little on Kotlin here, our last example is going to dig in a little further on that side. So the original time when I gave this presentation, Project Loom was still just in its early infancy. It has now arrived, or very nearly arrived, with Java 25, and it provides virtual threads. And virtual threads allow for work to be paused and resumed potentially on different threads without you having to spawn a full OS thread to do that. Now, the way that Loom does it is actually is pretty interesting and is very tied to I/O, because those are the big cases where you care about it. But the place that we're going to go with it to do some bytecode spelunking is that Kotlin had a feature called coroutines long before Loom ever got anywhere near the JVM. Like, versions of Kotlin that were capable of running on Java 8 had coroutines, and coroutines were able to do a lot of the same things. So how did they pull that off? How was Kotlin as a language able to build coroutines on top of the JVM when the JVM didn't have virtual threads as something to make available to them? Well, let's take a look. We'll start off by just sort of showing the code to run some coroutines and talk through how that would actually execute at sort of the high level. And then we'll take a look at the bytecode and see how the machinery really works here. So a coroutine gets started in Kotlin. You have to define a particular scope. There's different ways of doing the scoping. Here we're just doing a global scope. You say launch, and then you call various methods and do your work inside of it. The trick with it is that you inform Kotlin where the points are in the execution where you want it to be able to pause. And so the coroutine would start. In our case, it would call first, second, and then third. And at each of those junctures where it's calling that function, there was an opportunity when that function completed for work to be done on that thread instead of what we were intending to do next. So the thread could be cooperatively interrupted to be able to share work around. So each of those points were a potential pause. Now, Kotlin does this with a keyword called suspend. And this is actually a big difference between coroutines and the way that virtual threads have been implemented with Loom, is that this is a language keyword that you can use in Kotlin, and you can do it with potentially any of your methods that you want to allow interruption around. A lot of things in the library already have that built in. With Loom, it's more restrictive. They have chosen the things in the JVM, which are the things which will signal that there should be some sort of task switching, and you don't have direct access to control those. So coroutines in some ways are a little bit more generic and flexible potentially, but there are reasons for the way Loom went with their design. So we want to understand how did they do this magic though? How did Kotlin have coroutines on top of the JVM when the JVM itself didn't necessarily support it? Well, first thing that we notice if we go and compile this code is that normally when you compile a Kotlin file, there are various other things that do it, but like most of the time you compile it and you get a class out. We defined a class there, you get one class out, but in fact, we're getting multiple class files out. So that already gives you some hint that like Kotlin is doing something, like it's up to some tricks here that we're going to dig into. So the first file that we'll look at is the coroutineskt.class. And if we look into that, we'll see our main method. So this is the sort of representation of our main code file. This is the main, theoretically, that we wrote with that global launch in it to be able to get our work done. But this has a lot of stuff in it that's not exactly how we wrote the code, which is kind of interesting. So first thing, it goes and gets the static. This is the it finding that global scope that we were asking for. So it goes and looks up the static field. That's not too magical. But if we look down here on line 11, 8, 11, and 13, we see it instantiating an object. It's newing something. And there was nowhere in our code that there was anything getting instantiated. There was no new call in that. We just said global launch, first, second, third. And those are Kotlin supports just having like top level functions that are off floating and not attached to things as methods. So like there was no object instantiation that we did. If we look at the name of the class that's here as well, you'll notice that it's this $main $1 construct. That's sort of how it gates to make sure that we're not having colliding names for names that it generates behind the scenes for us. So it appears that Kotlin has created some whole class, some object that's doing something here, and it's instantiating it on our behalf when we write our global launch method. Now, when we get down towards the bottom, we'll see that this doesn't invoke static, and the method that it's invoking is the launch. So this is like the actual global scope.launch call that we make. And if we dug into the parameters and exactly how things are laid out, we would see that weird object that got constructed is being passed into this launch as one of the parameters. So things in the code don't directly look like exactly the bytecode that Kotlin is choosing to emit for us to be able to build up this structure. So that's part of the mystery, but we really got to know, like, what is that generated class doing? Like, that's obviously where the business is. That's where it's doing something interesting, because we didn't write that class. Kotlin made it up for us. So what is going on inside of it? Well, if we look in that class, as mentioned, we didn't write it, so we don't have methods that we know about to necessarily look for. But it's pretty obvious once you get looking that the key part about it is a couple of methods called invoke and invoke suspend. Those are part of this class. And the biggest thing with invoke is just that it calls invoke suspend. And we remember that like this has to do with suspended methods in Kotlin, right? We marked first, second, and third as suspended. And so this smells like we're kind of headed towards where something's going to happen about how it coordinates those method calls for us. So If we dig in and we go look for invoke suspend, we will find that that is also a method that Kotlin has implemented on this class, this made-up class that it's got for us. And one of the things to see on it, so it's going to load a load 0, so that's loading this object itself, and then it's getting a field which is not very nicely named I. So it's getting this field, and then it's going to do some work with it. So that field is going to be zeroed out to begin with. And what it's using it for is this table switch. So the table switch is basically a big glorified goto, right? So rather than saying go to 2, you say if the value that's on the top of the stack is 0, go to 40. If the stack has 1, go to 63. If the stack has 2, go to 88. And so forth. So it's sort of a concise way of representing a set of sort of jumps that you might want to do. So when we start, we're going to have 0 in that field because nothing's actually set it. So what's going on at byte number 40? Like that's the next sort of crux to the problem of figuring it out. So if we go look at the code that is between byte 40 and byte 62 before the next one, where 1 was pointing to 63 for us, we'll see there's some stuff that's like, it looks like some error handling. There's sort of a check cast. It does some odd loads here and there. But then on line 53, we finally get the meat of the thing. It's calling our method. It's calling our first method. So this is where the coroutines finally work their way through. It's gone through this intermediate object. It's sort of tracked with this table where to jump to next, and then finally called the first method for us. Now, right before it called the first method, we'll see it puts the constant 1 and then puts that into the field on the object. So it's executed this function, or it's going to execute this function, and it's marked that it's time to go to the next spot. So it's kind of a state machine. It has figured out where the various bits are supposed to be called and broken them up into these separate sections that it can then invoke one by one at will. After we've done the work from the first method, then we finally return back out. And so we would return from invoke suspend, and whoever called invoke suspend, which is library code that's in the Kotlin standard library, has the opportunity to decide what to do next. It could call invoke suspend to call the next step on our coroutines, advance the state machine and move to the next thing there, or it could give control to something else and do some other computation. So that's the principle of the coroutines allowing things to be sort of intercepted in that way, is that the Kotlin compiler has sliced it up into these chunks of bytecode for what to execute, and then arranges those through a state machine so that it can control the execution of it rather than it just being one method that it goes and calls. So it's cut the whole thing up into parts behind us, and we can see from the bytecode how it did that chunking and how it tracks how it needs to walk through it. So it's an interesting sort of perspective on it. It makes it very practical, very, very tactile, the way that it does this work by how the bytecode gets broken up. So those are the examples that I have of things that I have found value in digging to a deeper level into bytecode rather than trying to abstract away and step further away from my problems to try to understand how they work. So tonight we've talked about how bytecode gets interpreted and how the JVM runs. We've learned just enough bytecode to be a little dangerous. And I encourage you to go run Java P if you haven't on some of your own classes and just see what's in there. And we've seen how little we really need to know about those topics before we can understand things about concurrency and recursion and complicated structures like coroutines that Kotlin provides that honestly sometimes can seem kind of magical. So that's the talk. And what I've really enjoyed finding out with things is that, you know, it's always worth digging to that lower level if you can. And with Java, it's great that all the tools to do it are right there in the box and available to all of us. So thank you.
Okay, well, thank you for the talk. Does anybody have any questions? If you do, you can use the Q&A option. And so if you look at the bottom of your screen, for those of you who are in the meeting, of course it won't work in the recording, is there's like a 3x3 little grid of dots. It brings up a menu and you can choose the Q&A option. So while we're waiting for questions to come in, I've got a few.
Mhm.
So you showed us how to use this -C option or -P option there that'll print out the bytecodes there out of your class file. What if I want to go the other way? If I have a text file that has all this code written out and I'd like to create a class file from that, is there
Mhm.
kind of the equivalent of an assembler for the Java virtual machine?
I am not aware of one. That doesn't mean that it doesn't exist. There are definitely sufficient APIs in the JDK that would be possible. Like you can absolutely emit bytecode, like construct a class file from whatever arbitrary stuff you want to through some of the class file APIs. So I would actually be surprised if someone hasn't made something like that, but I don't know what the name of the tool is off the top of my head. So it's a cool idea to be able to
Right. Basically,
experiment with
it's
it.
like the macro assembler for the virtual machine. Is what I
Yeah.
was thinking you ought to be able to do. Now, when you say there are APIs, I can just write a Java program and just start calling these APIs, and what this bytecode is just going to show up in the memory somewhere, the Java virtual machine.
Yep. Yeah.
Because
Yeah.
it sounds like what I could do with that is to create self-modifying code.
Yes. Absolutely. And that is very much part of the JVM, that class, that transformation stage that I showed in the early going, like it is completely possible to rewrite what the bytecode is that's being loaded, generate classes on the fly that didn't exist in the thing, load a class file from some other location apart from your standard, class path. Like Java is, I mean, some people are like, oh yeah, it's statically typed, it's really stodgy. It is actually a very dynamic environment. And things can be rewritten on the fly. Absolutely. Like I worked for New Relic for quite a number of years, and the instrumentation that their Java agent does, it is rewriting your bytecode when it loads the classes. That is how that works, is it's injecting those things and putting wrappers around to do timing and instrumentation. So that is fundamentally part of the Java platform, that's a possibility. Terrifying as well.
Yes. What are the security implications of that?
Yeah, and I will say some of those sorts of operations you do have to opt into. And there has been movement in the recent past, a couple of versions that they may be moving to make it so that you, like right now, you can pass a Java agent by default, and it will run, and it allows some of these things, and they're looking at closing some of those down. If you're in an environment where you don't want it, I'm pretty sure that you can configure things to disallow it. But it is in the platform that the platform is, willing and able to load bytecode from locations other than just your class path if you wanted.
Yeah, you could just create any old thing that could do no telling what nefarious operation.
Yes. Or extremely useful and friendly
or maybe
operations,
very
like
useful.
timing your web server, right? It's a double-edged sword there.
Okay.
Cool.
I noticed that you're using a lot of these return instructions, this a return, that return, so forth. Where are those return values being stored? Because normally when I think of assembly language, I'm thinking of you've got to store the return address, which is the instruction pointer, or the it's known as the program counter.
Right.
It's got to be stored somewhere. I see it looks like you've got two stacks here. You've got one that's showing where your parameters and your return values are. That's your stack frame. And then you've
Right.
got a separate evaluation stack
Mhm.
where you add and subtract and multiply and divide and do all your
Yeah.
arithmetic and all of that. But where are the return values going?
Yeah, so the return values, a return value from something. So like this is a bad example because it's the one that never hits the return. But
Yeah.
if you call a method and it has a return, the result of you calling that method is pushed onto your evaluation stack. So that's the protocol, is when you call the method, if it has a return, that's going to end up on your evaluation stack from when the other frame goes away. So that's how the JVM sort of orders that. It's it's taking care of that for you, like unlike in like C like languages where it's just the stack is some contiguous memory and you just got a pointer to somewhere. Like the JVM manages that all internally for us. But the invokes, where if you have invoked a method to create another call frame that you're coming back from, the JVM makes sure that whatever the return is from that method is going to end up on your evaluation stack.
So there's positions in the evaluation stack that aren't actually shown in the diagram. They're showing like the effective program counter, because it's got to come back to the point at which you called. And it's got to remember that.
Yeah, and the JVM is tracking that. So like you are very right. Like my diagrams here are very focused on the execution while we are in a frame. I didn't really spend a lot of thought and time about like how we move between them. But that's mostly managed. That's managed by the JVM. It's execution as a stack, stack machine of stack machines.
Okay.
Like
so
it's taking care of that.
There, it's just not shown on the diagram, basically.
Yeah, that's
Okay.
It's outside the frame here somewhere that the JVM knows. I mean, I had the picture where there's a huge pile of them. It's like the JVM knows how all those call frames go together. Like it's holding on to those and knows who called who and who should I go back to and all of that. So it's kind of in the third dimension of the diagram.
Okay. Does anything special happen when you're doing like a lambda expression? Is it because you've got the surrounding context of the lambda and you have these, I think they call them effectively final, kind of put in quotes, values that you can access outside that lambda? Is it pushing something onto the stack and then reaching back into the prior stack frame? What's it?
That is a great question, and I don't know off the top of my head. I would go write a little Java program that just has a lambda in it and Java P it. It would not surprise me if the lambda-ish part of things is. I think that there were some special invoke instructions that were added for lambdas. So I believe that there are some things around that might be at play there. But yeah, I suspect that it would look different under the covers than you might think it's going to, though.
Right.
Like I'll have to go try that.
It would be an interesting experiment to perform, right? Because you could just write a simple program that has a lambda in it and just take a look at what came out.
I mean, I would love if folks went away from this talk and did exactly that. That is mission accomplished for me. If you go, hey, what would that look like in the bytecode, and go dig in.
I'm thinking of an inner class where you define an inner class that you would call from the outer class. You call a method in the inner class, and then you reference a variable in the outer class. I wonder if that might reach back into the stack frame to make that effectively happen. I was looking at code. I may have looked away, or you may not give it much time. But you had an example where you're modifying an object. We're modifying the bank balance on the other account, because that would have to go and call a method. It'd have to set the variable in the other object.
So, and that's where it does.
The put field has to take two operations, I guess. One object and one
Yes,
of the
that's correct.
values got put in. Yeah.
Yeah, that's its protocol, is that it expects the value that's going to be put to the field, and then prior to that on the stack, the object that is the destination, the instance for the
Oh, I
field.
see. The
And so when
the-
you call put field, it will pop those two values and do that operation.
So the
That's
H3 load and the dupe of it creates two copies of the object on top of the stack. So it uses one get field here, which uses up one copy. It
Yep.
does the load, it does the add, and then it has one HERN in the other object. Okay.
yeah.
That makes
It's
sense to
really
me.
it's really sophisticated and cool to me how it lines all that out so the stack ends up in just the right order.
Yeah.
Like how the compilers figure out that it needs to, dupe the things because I know I'm going to later need the value to be under the result value. It's pretty clever
Okay.
how it does that.
Thank you very much.
Yeah, there was a question in the Q&A about how bytecode looks with Java reflection. And that's a really good question because the reflection is one of those other sort of like dynamic sorts of things. And the answer, as far as I know, and you can always Java P and find out whether I'm right or not, is that like reflection is just another API. So it's just method calls. And so I would expect that if you're doing some sort of reflective sort of activity, you're just going to see objects that you've got and then calls to the reflective methods that you're calling with parameters going to them of whatever it is that you're handing in. I don't think it actually needs to do anything super sophisticated in most of those cases. And then it's the JVM itself has the implementation of like, okay, how to do the reflection. Like the complicated stuff is baked into the JVM itself. It's in the reflective code that says, hey, when you call invoke, I don't remember if it's called invoke, but right, you call invoke method, it is doing the internal stuff to be able to invoke the method. So I don't think that there's actually a lot of odd bytecode at that interface, because the whole point is that it is an API that is at the JDK level, just working for you in Java. But it's a really great question to like figure out whether my intuitions on that are correct, because I will admit I have not written a little program with some reflection and then taken a look at the bytecodes to see what they look like. So there could be surprises in there.
Okay, I'm looking at your diagrams for your call stack, and you have these slots. Of course, 0 is the this pointer. If it's just a regular method, if it's static, of course, there's no this
There would be none.
reference,
Yep.
of course.
Correct. Yep.
Right. But as far as how many bytes are in that, these are 32-bit quantities. So 0 is 30, like in your diagram there. This pointer is a 32-bit address, I guess.
Yeah.
And then all the others are 32 bits, because you're saying that amount was a long and it took two adjacent ones. Okay, but Java has built-in types like byte and short. And what's going on there? Is it allocating the full 32 bits and only using 8?
For the local stack, for the local argument passing, yes. Yeah. As far as I'm aware, those slots are homogeneously sized and they're 32-bit. And so if it's passing in a byte through it, I mean, it would put the value of the byte in there, and then it would, the bytecodes are generated from the knowledge of the types in your program. So when anything works against that slot, it's going to work with something that is aware that the value in it is a byte and do the correct thing.
So the other 3 bytes basically are just wasted.
That is my understanding. Again, that would be a pretty easy test program to write and see, give it a byte and then another byte and see what the loads, do with it to use those values. So if it still is like load 1 and load 2, yeah, it placed those bytes in those slots, even though they didn't consume all of the necessary space in them.
Okay. Now, Oh, we have a question posted in QA. That's an interesting point. Whoops, it went away there. But I was actually going to follow up on that and say it would be helpful. You've got diagrams that look at what your evaluation stack and your call frames look like. But what does an object look like when it's laid out, and what does an array look like when it's laid out? So if it's an array of bytes,
Right.
is it just wasting all of that, or are they really bytes?
Yeah, no, yeah. So objects or arrays, they would be strictly referred to by reference in these slots and on the evaluation stack. So you would have that, like that array would have been dynamically allocated somewhere else on the heap. The object would be somewhere else on the heap. And so they're always just references to that location, pointers, effectively. So anything that is not like the short list of primitive types, you know, your integers, your bytes, there may be some specialization around arrays in the bytecodes. That I may be not totally right on that, because those are old enough, like those were in the original language, so they may well have specialized bytecodes that do something. But I don't think that the way that the slots are used, I can't imagine that it would be like, yeah, if you pass 1,000 element array, it's using 1,000 slots on the call frame. I like that. Just
No.
It
I don't
seems
think
nonsensical.
That's not what I'm saying. Yes, you would have on your evaluation frame a 32-bit quantity pointing off somewhere in the heap where this thing is going to sit. But what I'm saying is, what is that pointing to on the heap, and what's the layout of that on the heap?
Totally. Yeah.
What does that look like? Are we looking at something laying on the heap where if it's 1,000 bytes, it's really laid out 1,000 32-bit words? You know?
Yeah. No. And I think that the allocate, that I think is different than these slots that are on the call frames. I do think that it doesn't waste. If you make an array of bytes, I think that the heap allocation for that is done in a way that is more efficient. But that's I don't think that what we're seeing with the slots here, and what I'm suggesting is how that works is like everything. I think the dynamic memory allocation is, I think with Java objects, there is a little bit of overhead for the object. Like there's a header that comes with it, and then the raw data. And I think that it is like, for an array, it is, if you had an array of bytes, it would be literally the number of bytes long plus whatever the header is should be what that'll look like. I believe the Well-Grounded Java Developer, not to keep pushing my own book, but there is some stuff that talks about object layouts and some of that deeper sort of stuff in there. And it definitely, there is material around, on the web as well about like how the JVM lays those out at allocation time as well. Lists, then those are an object. So you've just got an object wrapper. But arrays are kind of interesting because they are actually like typed in the JVM at that level. So they might get a little different treatment.
I would think an object would have to know not just that it's in object, but what the class of the object is, what its type is, because you can do runtime checks as far as what that is. And which method gets invoked depends on what subclass of the method is. So you've got to have 100%. Pointers somewhere to show you which method you need to invoke on that object.
And that's part of the object header. Like that is definitely why the object's like part of the object header is that it knows the class that it is coming from. And those invoke methods, like some of the variety, like there are actually, I think, methods which are like, no, invoke exactly this. But there are flavors of the invoke which are like, go find the right invoke through the method chain, and then that calls into the JVM's mechanism for doing the right dynamic dispatch that happens there.
Right. To make dynamic dispatch work, you're going to have a set of pointers for each class, but you don't have to repeat it on every instance. You can just have it in some global static space for that class, and you just have it in an agreed upon reserved area
Yep.
So it knows for this class, you look at offset 5 and that's the pointer to go call that method on it or something. Or, oh, you can reuse it. He didn't change it. You know, you can just use the inherited version, you know.
Yeah.
Okay, we had a couple of questions from Chris. I think you might have answered the first one. Interesting point. I'm guessing array versus list. I'm curious to see how that looks. I think you probably covered most of that. And the next question is, I'm guessing that the frame slots are sized by the 32-bit / 64-bit JVM. I'm wondering if I'm not sure if I exactly asking this question, whether the slots different sizes for the 32 or 64-bit JVM.
I don't know off the top of my head, honestly. I don't have a 32-bit JVM to test it on. It definitely, like, the impression that I get from the way that the bytecode's ending up laid out, though, it seems like the slots are 32-bit. Because it's, you know, an integer fits in it and it uses 2 slots for the long. So I suspect that they may well have just kept that slot alignment.
Your backwards compatibility.
Yeah, which is, of course, such a huge thing in the Java ecosystem. So the evidence that I see suggests that the slots are even on a 64-bit machine like I'm working on, or 32-bit.
Okay.
And if I remember, does your book go into any detail about what the layout of a class file actually looks like, as far as when I'm going to load that thing? Because, you know, the thing they drill into our heads on Java exams is that there's this magic number in hexadecimal. And I bet some people here probably remember what the magic number is for a class file in hexadecimal, what it spells out.
Yep.
You remember?
Yep.
Say it.
Cafe Babe, yeah?
Yep, Cafe Babe.
That's the one.
So it's got to load that. First, it's got to determine, is it even a class file at all, or I'm just not even going to run it, right? Because it didn't have it didn't even have the right magic number. But then I think it's supposed to go through some sort of a validation process beyond just, did I have the right magic number? And I don't know what the JVM is doing to actually validate a class file, because I don't think I can just write a string of bytes and start off Cafe Babe. And then after that, here's just some random integers and somehow expect that the JVM is going to run that thing.
So this is definitely a topic that is covered very well in the Well-Grounded Java Developer. There's a whole chapter that's on class loading and the verification process. And yes, the JVM does very much have a lot of safeguards where it checks through a variety of mechanisms that everything is lined up the way that it's supposed to be. And I mean, that makes some sense when you look at this, where it's like, okay, it's making assumptions at this point when we're executing of, like, I'm getting a byte off of this, and then I expect that was an integer, and I'm doing these operations. That is safe because at load time, the JVM is able to do verification activities on it to be able to know that, you know, the bytecodes are not malformed and not going to do something nefarious. So yeah, if you take a class file and you try to monkey around with some of the bytes, you have pretty strong odds that the JVM is just going to give you a thumbs down on it when you try to load it and refuse.
Okay. And I gather that those checks are going to run when you're doing this dynamically as well, because you mentioned in my earlier question, if you say there's an API where you can just generate bytecodes on the fly, is it going to invoke the security check to make sure that I didn't just create some sort of no telling what garbage in the memory, not necessarily in a file?
That's part of class loading. Like, it is fundamental to when a class gets loaded into Java, and those APIs that I was referring to, they're just another entry point into some flavor of class loader that eventually is going to ask the JVM to do what it needs to do. So yeah, you can't circumvent those verifications by, by those APIs.
Okay. All right. Do we have any other questions? Did you see any come in, Ted?
No, I haven't.
Okay. Well, this is actually a very interesting topic because in so many presentations of ours, we talk about this cool thing and that cool thing, but, what is it really doing?
Yep.
It's like,
And
and
this may not
we
be
never really
eventually what it's
tackle
really
that.
doing. Yeah. Yep. I mean, JIT puts a whole other layer on top of it, but this is getting pretty close to what it's really doing. Like it's part of what I've loved about digging into this stuff, just how,
Okay.
how that works.
Okay. Question: do you see different bytecode with Oracle's JVM versus another?
So it's less about the JVM and it's more about the version of the Java compiler, and it absolutely varies between versions. Probably not on some of these fundamentals, like if you're just calling a method that's adding two numbers you passed in, probably going to be identical. But there are definitely distinctions between different versions and the bytecode that will be emitted. So that is something that it continues to evolve over time. They're not adding new bytecodes very often. There's actually, I think, kind of a hard limit. I think it's 256 of them, I think, or something, that they have a max, and they're getting closer than they'd like to be already. So it's not something where the bytecode set evolves very quickly, but the compilers do generate different sorts of bytecode. And like as the JVM gets better at optimizing certain structures, the compilers are learning to, emit patterns that are going to allow for better optimization, handling when new features come into the JVM, leveraging those. Obviously, you'd end up with different bytecodes than before, but yeah, it will not be the same across JVMs and JDK versions. No guarantees on that. Your only guarantee is that if you've compiled it for a certain version of Java, any JVM after that will happily accept your bytecodes. That's that will work, but yeah, you're not guaranteed that it's going to spit the same thing out for you.
Okay. Yeah, I noticed one of our guests here has pointed out that there's a Wikipedia article that lists
Yes.
all those bytecodes that are out there. I'll have to look at it.
Yeah, it's good reading.
That are not currently assigned are Charlie Baker through Foxtrot Delta. So that's hate to do math. I'm thinking that's 32 bytecodes that haven't been assigned yet. 256.
That sounds roughly like what I remembered it saying. Yeah, the documentation as well, the JDK docs on the bytecodes, if you go look into the spec, for the JVM, it wouldn't be JDK, it'd be the JVM spec. They are actually relatively approachable. Once you've got sort of these foundational ideas of what's going on, they do a relatively good job. And they are very, very precise. Like all that stuff we were talking about of like, oh yeah, the things have to be in this order, it pushes and pops into like, it is all spelled out in every bit of detail that you could want there. So.
Okay. Where does the garbage collector fit into this? Is the garbage collector getting some hints or something from the bytecode so it knows when the last reference to something is going away, that the garbage collector can actually kick in and free up that memory?
I mean, I think my understanding of the way that it works, there's not really anything that's bytecode related with it. It is more on just the heap allocation side of it, and that there's tracking that understands, like, the program knows root objects that it can guarantee exist, and any object that is still alive is going to have a reference that you can reach from it. And so it effectively just spiders out and walks the heap structures to find all of the references to anything that's there, and it marks the ones that it knows that it's seen and cleans up the ones that it doesn't. But no, there's nothing at the bytecode level like we saw. It's like, well, you know, it knows it, it's pushing that reference around. The fact that that reference goes away after, there's nothing in the bytecode that's indicating that. It's by usage alone that it would figure that out.
Where would I look to find where the starting garbage collection routes are? If I was trying to trace this by hand, say, okay, where are the routes?
I don't
And
actually know where that is. Yeah.
Spinning off from there.
Yeah. That's a really good question. I'm not sure off the top of my head exactly where you get those. Not to pitch my book yet again, but Ben wrote a really excellent topic on garbage collection. So if you want to, like, that's probably a pretty reasonable starting spot for more details on it. I'm not saying everything's in my book, but everything that I talk about is pretty much in that book.
Okay.
So, you know.
Maybe you need a third edition.
Yeah, we're scheming. We're scheming.
Okay. Okay. Any other questions here? Ted, are you seeing any?
No, I'm not.
Okay. Well, if that's all the questions, then this is usually where we'd have a big round of applause here for our speaker.
Thank you.
So thank you for coming on. And I'm going to click this button and stop the recording.